All right, everybody, welcome to the video on 6.2, areas of cross sections. We've already done section 6.2 before, but we did not talk about cross sections. So far, we talked about the disk and washer methods, and both the disk and washer methods were based on the idea that you were taking the volume of cylinders. So we were taking volumes of cylinders, either with or without holes in them, and what you were doing is you're finding the volume of these things and adding them up. Now, the width was always the delta x or dx or dy, depending on which orientation you had. And then you obviously had the radius. And the reason we use cylinders, that's how we get the formula. Pi times the radius squared, it's the area of the base, which is a circle, times the height, which is delta x. Or depth, actually. Height or depth is how we want to think about it. This method can be generalized to solids of any shape. They don't have to be cylinders. Instead of rotating, you can imagine that the shape is being built with cross sections of different shapes. For instance, squares, rectangles, trapezoids, semicircles, and triangles. The only area I want to remind you of is the area of a trapezoid, which is 1/2. It's the average of the bases, b1 plus b2, times the altitude height. And so what that would look like if I had a trapezoid, they're usually isosceles trapezoids, which are basically truncated isosceles triangles. H would be this distance here, the right distance. This is B1 and B2, the parallel bases. You'd add those two bases together, divide by 2, multiply by the height. And therefore, if you want to find the volume, it would be the same thing. Base 1 plus base 2 divided by 2 times the height times the depth, which would be a dx or dy. And that would look like this. We had just an isosceles triangle with some depth to it. And that little wedge on the outside would be the delta x. Getting right into it, this is what it would look like. For cross sections of area A of x, where the functions in terms of the variable x that are perpendicular to the x-axis would be, the volume is equal to the integral from the a to b bounds, these are going to be x values, of a function with respect to x, and then times dx. So you're integrating with respect to x as well. So here's the idea. This function here, if you're not visualizing it, it's actually the x-axis here, the y-axis there. And so on the cross-section here, if I were just to view it how I normally view it, it looks something like this. So that curved line is what I just drew there. And you can see visually the red cross-section there is vertical or perpendicular to the x-axis. Now the same thing can be shown down here with respect to a function in terms of y, and perpendicular to the y-axis. It's the same idea. The volume now will have different bounds, which are going to be y values. The area of a function, basically the height of the function area of a function with respect to y, dy. You're going to integrate with respect to y as well. And again, to give you a picture, if you're not a visual person, y, here's x. And again, we're graphing a very similar shape to where this is just a little bit higher, it looks like. And now the rectangles are perpendicular to the y-axis. Instead of rotating like we did before with the disk or a washer, I'm basically just going to pop up a shape. And you can see that this shape looks like it's a square, and this one is almost like a trapezoid up here, but I'm not really sure with this curved side what that would be. Here's an example. This example is in the book as well in section 6.2 if you'd like to follow along with that at some point, or if you just prefer to look at that later, it's in there. It's sometimes helpful if I am here to talk through it. So we're going to talk about how we find the area, or volume, excuse me, the volume of this big blue triangular pyramid it almost looks like. Now, the volume, as we saw before, is just going to be the integral from some a to b. And now we need to make a decision. Is this function in terms of x or y? We can see that the shape, when I plot it, if you're not a visual person, there is the base here. And I'll put a star for a reference point. The star is right here on this picture. And there's the point. And you can see that my shape base, the base of this cross section, this triangle, is perpendicular to the x-axis. So this is going to be a function with respect to the variable x. And we're going to integrate with respect to the variable x. And that means a and b are going to be x values. Now those x values, it appears it's going to, are from 0 to 2. Now we have to find this a of x. And to find a of x, you need to draw a picture of the cross section. In this case, it's an equilateral triangle. Some things we know about equilateral triangle, all the sides are congruent. every angle is 60 degrees. If I draw an altitude down from the top, it's going to bisect that top angle and make a 30, 60, 90 triangle. Now to find the area of this thing, the area of that thing, it'd be 1/2 the base, 1/2 this base, times the height. Now the height, because it's a 30, 60, 90 triangle, is easy to find. I'm just going to draw this little thing here. So that's going to be from this part. Now this is going to be 1/2 the base here. Now the height, now this is a 30, 60, 90, so this proportion is going to be 1. If you remember from geometry class, then it's going to be 2, and then the square root of 3 times the small side. Now the small side is 1/2 base, so it's going to be 1/2 base times the square root of 3 times 1/2 the base. Because you take this proportion times the square root of 3. 1/2 the base times square root of 3. I'm going to get the square root of 3 over 4 times base squared. And that would be the area of the cross-section. Now, if I put it with respect to x, that means I have to measure the base in terms of that function length x. So to find that function length, you can see here that the base is the difference between the top function and the bottom function. So it's going to be f of x minus g of x. And I should move over so I have some room, so I'll hopefully didn't start drawing right there. But f of x minus g of x is what I'm looking at in this particular example, because the f is higher on the positive y side than the negative y side. So that means we have 1 minus x over 2 minus the quantity -1 plus x over 2. That means that 1 and positive 1 would make 2. Negative x over 2 minus another x over 2 would just be minus x. So that is the length from this base. That is 2 minus x from the very top to the very bottom. 2 minus x. And then we're good to go. So we plug that in to our area of x. It's going to be the square root of 3 over 4 times that base, which is 2 minus x. That should go in here. Oops. That's not good. Better finish the video. 2 minus x squared times delta x. I could pull that constant out in front, so I'm going to just take the square root of 3 over 4 out in the front. And it's integral from 0 to 2. Now I just have 2 minus x squared, which would be 4 minus 4x plus x squared dx. This is a pretty convenient integral for me to do. So I'll go ahead and do that. So it's going to be 4x. And again, I have to use the fundamental theorem of calculus here. Minus 2x squared plus x to the third over 3. And I'm going to evaluate that from 0 to 2. And again, we're conveniently bounds at one of them 0. So it's going to make my life a lot easier when I have to use the fundamental theorem and subtract the second side. So the first side will be 4 times 2, which is 8, minus 2 times 2 squared, which is, again, another 8, plus, now this is going to be 2 to the third power divided by 3, so it's going to be 8 over 3, minus the 0 from the other side when I plug in 0 to all those things. So that means I have the square root of 3 over 4 times 8 over 3, because these 8's are going to cancel out. And this is going to reduce to 2 and 1, so it's going to be 2 root 3, square root 3, I should be specific, units to the third power. That would be the volume. You can approximate that with a calculator if you'd like. Let's move on to the last example. Now, you might wonder, maybe you don't because you're not really into it, but when I was in geometry class, I wondered how they get these arbitrary formulas. Like, oh, the volume of a pyramid with a square base is volume equals 1/3 h times b, where h is the height of the pyramid and b is the area of the base. And let's prove that. And we can prove that by using this method. Now, you can see the cross-section of this is going to be with respect to y, because you can see, again, for those of you who aren't very visual, what's happening here is I have the x-axis there and the y-axis here. Now the cross-section I'm going to draw with gold right here. That's that cross-section that they did right there. You can kind of see right there what's happening. Now, in terms of this cross-section, we can find an area by using the similar right triangles. And so what would happen here is, you can imagine if I put the other side of this here, just going to kind of sketch in what the other side of the triangle was. If you use similar right triangles, it's apparent that these two sides I just put dashes through would be similar. And so the length here, this total length there would be b prime, and that's the length of the small base where my cursor is. If I had the proportion of that over the entire long side of this base, so there's the base right here, the capital B, we'll say. And that's going to be equal to the proportion of the small height of this tiny triangle up here compared to the whole height of the triangles. So that would be, the small height would be h minus y, the entire height would be h. And so that means if I cross multiply here, that would mean that b prime, the small base, would be equal to capital B times h minus y over h. Now the cross-section area is a square, like this. And it's that b prime right here, you can see from the picture, that if I wanted to find the area with respect to y, it would be b prime squared. So I'm just going to need to square this thing down at the bottom there, which would just be b squared, capital B squared, over h squared times that quantity h minus y squared. Okay, and some of this stuff is constants. So it's going to help us out. So when I take the volume of this, the volume is going to be equal to the integral, and it goes from, looks like, if we were doing it with respect to y, it's going to go from 0 to however far up you go, which is to h, times the area with respect to y, which is going to be that b squared over h squared, times h minus y squared, times dy. Now this b squared over h squared, that b is constant this entire time, and so is that height. And so you could pull out that b squared over h squared to the front of it. So b squared, capital B squared, over h squared, from 0 to h, of this h minus y squared, which would be h squared minus 2hy plus y squared, sorry, dy. We'll integrate with respect to with respect to y. Struggling today. And so if that's the case, then I'm going to get b squared over h squared, and then that's going to be h squared y minus, and this is going to be hy squared because I divided by 2 and I added 1 to the power of h. H is like a constant number, plus y to the third power over 3. Now I have to evaluate that whole thing from h to 0. And again, it's convenient that I'm going from h to 0 because that means the second half of this will be much easier. So if I do that, if I plug in h, that makes h cubed here minus another h cubed plus h cubed over 3 minus the 0 from the other side, fundamental theorem. So that means that if I multiply this all out, I get this stuff's going to go away, and so I get b squared times h cubed over h squared times 3, which then if you cancel the powers, it's base squared, oops, gotta hurry, h over 3, which ends up, if you rewrite it, as 1/3 base squared times height, which is what our result wanted to be. Now your homework for this evening, you work on the pages 430 to 431, 59A and B, and you can read the rest of that. Hopefully that all makes sense. Let me know if you have questions. Message me on Schoology. We'll have a quiz on this on Thursday, and I'll be able to answer your questions tomorrow during the shortened day. Have a great night.